Okay. Last week we finished the data preprocessing 01, and now we are entering the data preprocessing 02. So in the first part of the data preprocessing, we learn the data cleaning and data integration. Thank you. Now in this section, we will learn the data reduction and data transformation. What are they? Data reduction. We call data reduction because we want to obtain a reduced representation of the data set that is much smaller in volume, but yet produce the same or almost the same analytical results. So the simple idea is, last time I mentioned to you, if we have 1 million data, if we have 1 million rows data, and it produces maybe 95% accuracy, and I have 1000 rows data, and it produces 94.9% accuracy. It means with the very big data, maybe the computer needs to perform harder than the smaller data. So why don't we use the smaller data? Because it shows almost similar result in the performance. So we can try to use the data reduction. We don't need to use 1000, we don't need to use the 1 million data because we can just use the 1000 data. So we can see the reason why we need to do this data reduction. First, the database or the data warehouse may store terabytes of data. So if the database is very big, you cannot analyze all the data because your computer is limited, your laptop is limited. So we need to make a very efficient way. And also the complex data analysis may take a very long time to run on a complete data set. So we need to think the data reduction strategies. So there are some strategies you can learn. First is the dimensionality reduction. Dimension, do you still remember what is it? Dimension, we call it attributes, okay? Or we can call it columns, we can call it variables, okay? We can call it fields, we can call it features, okay? So those are the same name or the similar name. We want to reduce the dimension. It means we want to remove the unimportant attributes. Let's say I have 6 columns, 1, 2, 3, 4, 5, 6. I want to reduce it into 4 columns, 1, 2, 3, 4. So with only 4 columns, I can get almost the same result. We need to do something with methodology like Wavelet Transform or PCA or picture subset selection or picture creation. We have the second strategy, we call it numerosity reduction, or it is data reduction or instance selection. Instance, what does it mean by instance? It is the rows, okay, or we can say this is the objects, okay, or this is the samples. So those are the other names of the instance. Let's say I have what I mentioned before. If I have 1 million data, I want to reduce it to 1,000 data. So because this is the instance selection. There are some methods like regression, log linear models, histogram, clustering, sampling, or data cube aggregation. And we can also do some other strategy. We call it data compression. We have numerical data like this one, and we want to make it discrete. The discrete can be in the vertical, or it can be also in the horizontal. So this kind of way we can say it is the data reduction strategy. So the first is about the dimensionality reduction. What is dimensionality reduction? As I mentioned to you, we have features, we have columns. So we want to reduce the number of columns. We call it, this is curse of dimensionality. When dimension increase, data becomes increasingly sparse. You can see from the iris dataset, the iris dataset only have 5 columns. Now I'm working on the research with my students, and the number of columns, we have 500 columns, orbit columns. So how can I use those 500 columns? We need to reduce it to make it more interpretable. We need to reduce it to understand. Because if it is too big, it is sparse. We call it sparse. Because we cannot even understand. Maybe there will be many zero, or there will be a lot of meaningless values. Density and distance between points, which is critical to clustering or the outlier analysis, become less meaningful. So if it is too big for columns, it is not meaningful for making the clustering or the outlier analysis. And the possible combination of subspace will grow exponentially. So if we have this number of column, maybe we can just combine those columns, 6 columns. We can select among the 6. Maybe we want to choose 4, which is the best. But if we have 500, then how you can find which is the best features? It's more complicated. So the dimensionality reduction is necessary to avoid the curse of dimensionality. And it helps to eliminate irrelevant features and reduce noise. And it reduces time and space required in data mining. And it allows easier visualization. If you have one column, it's easy because you can just make like this. We have only have one column. If we have 2 columns, X and Y, we know the scatter plot. We can plot like this. If you have 3 dimensions, X and Y and Z, okay, you can still see. But if you have 4 attributes, it becomes more complicated. If you have 5 attributes, it's not easy to do the data visualization. So if you can reduce it, it will be easier for you. It can reduce the time. It can reduce the space. So there are some techniques on the dimensional reduction. Wavelet, principal component analysis, PCA, and feature selection. So let's see. Wavelet. We call it wavelet transformation. In some literatures, they call it DWT, discrete wavelet transform. It is used for the linear signal processing and then multi-resolution analysis. We want to compress. The idea is to compress something which is very big. We want to make it smaller. So start only a small fraction of the strongest. Start only a small fraction of the strongest of the wavelet coefficient. This is the method. I will show you with the example. I think it's easier. Because this is the wavelet decomposition. So wavelet is a mathematical tool for space efficient hierarchical decomposition of functions. Let's say this figure. The original figure is this lady. The original figure is this size. But maybe when you want to send your message in the Kakao, or you want to send message through email or through another messenger, but the size is too big, so you need to reduce the size. I want to reduce the size of this figure, but this figure should be the same. Even though the size is small, but I can still see the face. So what is the way to reduce this one? Then the wavelet is one of the ways. We call this is the data. Okay. Let's say I have the S is the data 2, 2, 0, 2, 3, 5, 4, and 4. So this is the data from this figure. Let's say if you know the RGB. Have you ever heard? That's why, red, green, and blue. Okay. So when you make a color, okay, if you learn about the science, well, you learn that every color is the composition of red and green and blue. How many red, how many green, how many blue, it will determine the color. So it can be also in numbers. So the numbers from 0 until 255 of red, 0 from 0 to 255 of green, and from 0 to 255 of blue. So every number will have different color. So let's say I'm using these numbers, the small numbers, to represent the pixel or the colors. So I have the resolution 8. You know, every picture will have resolution. If the resolution is 32, yeah, of course, it's bigger. If it is smaller, then the number is also small. So let's start with the resolution 8. So I have like 1, 2, 3, 4, 5, 6, 7, 8. I have 8 data. And I want to reduce it to resolution 4. Then, yeah, I can get only 4. I want to reduce it to 2. I can also get the resolution 2. I want to reduce it to resolution 1. Yeah, I can get this number. And after I get this number, I can transform it to an S hat, which is from this number to 3 divided by 4. And then I have this detail coefficient minus 1, 1 divided by 4. And then I have half and 0 into this half and 0. And then I have 0 minus 1 minus 1 0 into here. Because this is the transform from the wavelet. Compression means we want to have many small detail coefficient that can be replaced by 0, and only the significant coefficient are retained. I will show you how to calculate this one. So we have the original data 2, 2, 0, 2, 3, 5, and 4, and 4. This is in the resolution of 8. So if I want to reduce it to resolution 4, so I can just calculate the averages. How can we calculate the averages? We select the two components, 2 and 2. 2 plus 2 divided by 2. Then we put in the place of the resolution 4. We have 0 and 2. So we have 0 plus 2 divided by 2, and the result will be placed here. 3 and 5. We have 3 plus 5 divided by 2. We put the result here. 4 plus 4. We use 4 plus 4 divided by 2, and then we put the result here. So this is the reduction from the resolution 8 into resolution 4. This is the reduction. So we have 2, 1, 4, and 4. Now, how can I get the detail coefficient? If we use the plus for the averages, for the detail coefficient, we use minus. 2 minus 2 from here. 2 minus 2 divided by 2. So the result will be here. And then the next two, 0 minus 2 divided by 2, we put here. 3 minus 5 divided by 2, we put here. And 4 minus 4 divided by 2, we put here. Okay. Then we can get the detail coefficient 0, minus 1, minus 1, 0. How if we want to reduce this into the resolution 2? The same idea. We will get the average. 2 plus 1 divided by 2, we can get 1.5. 4 plus 4 divided by 2, we can get 4. What about this? It is the result of 2 minus 1 from this one divided by 2. So we can get half. And what about this? It is 4 minus 4 divided by 2. So we can get this value. What about this? The resolution 1 is 1.5 plus 4 divided by 2. And this is the number. How to get this one? 1.5 minus 4 divided by 2. 1.5 minus 4 divided by 2. We can get this value. Okay. Then we can get the transformation value from this, and then next this one, and goes up half and 0, and then goes up 0, minus 1, minus 1, 0. This is the transformation using the wavelet. We can create the wavelet coefficient, because this is the wavelet coefficient, because we can calculate each of the coefficient from the detail coefficient previously. So this is the numbers that you can create. The 2.75. It is from the this value. Okay. And then minus 1.25. It is minus 1.25. And then we have half. We have half, 0, and then 0, minus 1, minus 1, and 0. Okay. And this is the hierarchical decomposition structure, or we call it error tree. How can we use this error tree? Okay. Let's say I know that this is the original number. Okay, this is the original number, and we can extract this number from the detail coefficient. For example, I want to know this. How can I get this number? So actually this number is from the if we want to check from the upper part, okay, we can have 0. It is start from the -1, -0.5, and plus -1.5, and plus 2.75. You will get this formula, and the result is 0. So you can get for every of this value by calculating with this detail coefficient. It means if you want to reduce from the resolution 8 to 4, you can use this detail coefficient. If you want to reduce from the resolution 4 to 2, you can use this detail coefficient. Okay. So we call this is the Haar wavelet coefficient to determine how you can reduce your data. The other data reduction method for the dimensionality reduction, we call it PCA, Principal Component Analysis. We want to find a projection. Okay, the keyword is projection that captures the largest amount of variation in data. The original data are projected into a much smaller space, resulting in dimensionality reduction. Okay, you know the dimensionality reduction. We want to reduce the attributes. We want to reduce the variables. Let's say this is the original data set. Yeah, I can see this is a data with two variables or with two attributes, X and Y. Now I can see that this data is somehow in the linear space. If I want to change this original data into a principal component, maybe I can use the linear algebra. Okay. So there are some ways. I do not want to discuss the detail, but after we use the PCA, I can get this value in the range of 0. And we have also, this is the 0 point. And this data can be represented in a new way. This data is similar representation with this original data. And in other things, we can also use the n data factors. N, big N is the number of data or the number of rows from n dimension. So it means n is the number of attributes. Okay, we have n columns. Okay. So we need to find the k. K should be less than n. So if I have 5 columns, n equals to 5, then if I want to make the dimensionality reduction, I can start from the k can start from 1, 2, 3, 4, and even 5. If you have 5 columns, I can reduce, maybe I can make it 4 columns, I can make it 3 columns, I can make it 2 columns, or I can make it 1 column, or I can also still use the original column 5. So that's the meaning. And we can find the k orthogonal factors or principal components that can be best used to represent the data. So this PCA, it works only for numerical data. This is an example of the iris dataset. Suppose we want to reduce the features of iris dataset from 4 attributes to 2. I want to check only 2 principal components. So I have 1, 2, 3, 4 columns, and I want to reduce it into 2. Principal component 1, principal component 2. So below is the example of the first 5 data from the iris dataset. You know that this iris data has the sepal length, sepal width, petal length, petal width, and this is in the millimeter. 5 millimeter and 3 millimeter, 1 millimeter. So we can understand this one. But maybe 4 columns is too big. I want to reduce it into 2. So with the linear algebra, we can make it into 2 principal components. So if I know this data is isotonic, with these 2 columns only, with this number, it also can represent isotonic. So we got this method is the principal component analysis. Let's see with orange. So I would like to use the iris. Okay, in the file, I would like to use the iris. And then as you can see, this is data table. And then I know that we have sepal length, sepal width, petal length, petal width, and this is the iris data. So let's see if I want to use PCA. Okay, you can type PCA. So here you can see that the component selection, there can be some options. How many components you want to select? As I mentioned to you, there will be N and there will be K. Okay. K is the number which is lower than or equal to N. N is the number of columns. So if N equals to 4, what is the possible number of K? It can be K can be from 1 or 2 or 3 or 4. Okay. We can select all attributes, or we can reduce it into 3, or we can reduce it into 2, or we can reduce it into 1. If I use the component 4, so the cumulative variance is 1. It means it is the most representative data. Or I can say that when I select 4 components, it is the same with the original data. Now, if I remove it, now I want to choose 3 components. The 3 components, it represents 99.5% variance of the data. So it's still almost 1. Okay? Then it is good. What about if I remove it into 2 components? It shows 95.8%. So usually, people say that the threshold is 95%. If it is still above 95, then you can choose that color. If it is lower than 95, you need to consider. You need to consider the better value. Let's say I want to make the component becomes 1. So the X-plane variant is 72. So it's very low. As I mentioned before, it is good if the X-plane variant is more than 95%. Because it is 72, then it is not good. So it's better to choose the K between 2 or 3 or 4. If it is 4, then it is the same with the original data. Okay. So after you have this one, let's say I want to choose 2. Okay. Then you can see in the data table, there will be 2 principal components. So these 2 principal components is representing the other 4. It means rather than using 4, you can use only these 2 to know about the flower. So you don't need to use the 4 attributes. You just need to use these 2 to know about the flower. But as you can see, these 2 has 95.8% of cumulative variance. So not all the total population variance can be known. Okay, so this is the PCA. Okay. The other way to do the dimensionality reduction is to use the subset selection. What is subset selection? So we have, let's say, the redundant attributes. Redundant attributes means we have duplicate much or all information contained in one or more other attributes. Let's say, in any countries, you will pay tax. Okay? So if you go to 7-Eleven, if you go to Mart, if you go to restaurants, when you buy something, there will be tax. And maybe in your database, you have 2 columns. You have price and you have tax. Instead of using these 2 columns, it's need to use 2 columns. But actually, you can combine those 2 columns. Price plus tax is this number, this number. So it means you do not need to use those 2 columns. You can just use the column price plus tax for the analog. Because it shows the high dependency. Or we can say that these 2 columns redundant with this column. Attribute subset selection, it can also say the irrelevant attributes. The irrelevant attributes means contain no information that is useful for the data mining at hand. Let's say this is the data about score or grade. Student 1, in the course of mathematics, the grade is A0. Student 2, in the course of Heuristic, the grade is A+. So the student ID is often irrelevant. If you have only ID, is it meaningful or usually it is not meaningful because ID is unique. So if it is not relevant, you can just remove. So some other attributes might be irrelevant and you can determine based on your data set. We can use heuristic search. Heuristic search means we will find the combination. There are two power of the possible attribute combination of the attributes. Let's see this one. I have 4 attributes. So there will be 2 power of 4 possible attribute combination. Okay. If the number of attribute is 4, so there will be 2 power of 4. It will be 16 combinations. Now, we can choose attribute 1. It's one combination. We can choose attribute 2. It's one combination. We can choose attribute 3. It's one combination. We can choose attribute 4. One combination. And then we can choose attribute 1 and attribute 2. We can choose attribute 1 and attribute 3. We can use attribute 1 and attribute 4. We can use attribute 2 and 3. Attribute 2 and 4. And then we can choose attribute 1, 2 and 3. We can choose 2 and 3 and 4. We can choose 1 and 2 and 4. We can choose 1 and 3 and 4 and so on. So there will be 16 combinations. So because this is the 2 power of 3. 3 is the number of attributes. So there can be many ways. We can select the best single attribute under the attribute independence assumption. So you can choose by the significant test. You can select with the statistical test, for example. So we have 2 ways. Best stepwise feature selection. What is the meaning? This one. First, we can choose attribute 1. And the next, yes, is the best single attribute is pick first. So maybe from the attribute 1, 2, 3, 4, I can calculate with the correlation. You still remember correlation? Okay, with correlation, I can calculate. Okay, the attribute 1 is the best. Okay, I choose attribute 1. And then the second is, we can select the next best attribute condition. Maybe the most correlated attribute can be chosen. So maybe the attribute 4 is the next attribute we can choose. And then we run the data analysis, whether they give the good result or not. And then we select the next attribute, which is the best, maybe attribute 2. And then we select the next attribute that also the best, maybe attribute 3, and so on, until we get the performance that we expect. Because this is the feature selection, or the best stepwise feature selection. The other way is the stepwise attribute elimination. Elimination means we want to remove from the attribute 1, 2, 3, 4. We will repeatedly eliminate the worst attribute. So maybe the attribute 1 is the worst. So we will remove it. And then we will calculate again, check which one is the worst. Oh, maybe the attribute 3 is the worst. So we will remove it. Maybe next is attribute 2. Okay, we will remove it. Then maybe the only good attribute is attribute 4. Then maybe we will use only attribute 4. Okay. So this is what we call as the attribute elimination. We can combine between selection and elimination. Maybe after we have attribute 1 and 4 and 3, it's not good. So we will replace it with 2. So 1, 4, and 2. So it can be combined. The other way to do it, dimensional reduction, is to create more attributes. Create new attributes or features that can capture the important information in the dataset more effectively than the original ones. So there are 3 general methodologies. First, we can extract the attribute. It is a domain specific, very specific. For example, I want to know from the income, maybe I'm not sure what is the meaning by 5,000K, 2,000K, 2,000, 2,200. So I would like to make some new attribute. I call it category. If I know that the income is more than 2,000K, I think that I have a confidence this is a high target for the marketing. If the income is lower than 2,000, 5,000K, or maybe lower than equal to 2,000K, this is the low target for the marketing. So it is more representative, or it is more interpretable. We can know clearly that high possibility or low possibility. Another way is to map the data to new space. We learned about the wavelet. It is the data transformation or other transformation like Fourier transformation. Or we can make the attribute or attribute construction. Construct. We want to create. We can combine the features. Let's say this one. Last name, first name. We have 2 columns. So we can just make 1 column, full name. So we can combine Harry, Haar. So Harry. It will be reducing the columns. Or data discretization. So this is an example of data discretization. If the income is higher than some values, then we can say high. If the income is lower than some values, we call it low income. This is the data discretization. Okay, so let's see. In orange, you can use the features select columns. There's a select column. When you select a particular column, you can see here ignore and features. So if you choose the features, you will see only the chosen features. So here sepal length and sepal width, then only 2. But if you want to choose for all features, okay, so all 4 features, then you will see the all 4 columns here. So we call this is the select column. Next is the feature constructor. We have the feature constructor. Let me remove. So the feature, you can create a new feature. You can create a new column. Here orange define at least 4 types of data. Numeric, categorical, I think you know those 2, and text and date and time. Let's skip the text and date or time. Let's focus on those two, numeric and categorical data. For the numeric, I can make a new numerical. Let's say this one. I want to create a formula. Suppose, yeah, you can see this drop down. The left one is to select the feature, and the right one is to select the function. There are many functions like absolute, a cosinus, a cos, arcsine, and so on. Okay. So you can check those formula. So let's say I want to make a formula that this is x1 is a formula of sepal length multiply, yeah, I will follow this one, multiply by sepal width. Let's say I would like to multiply with 0.1. So I have this formula, just an example. So after I have this formula, you can click send. Then it will make a new column x1, and this x1 is based on your formula. Okay. And let's say if I want to make a new formula, I want to make a new numerical, and maybe I can say maybe small. Okay, let me make a small sepal. Okay. The small sepal means I want to make it 0 if the sepal length is less than 5. Else, what? So if the value of sepal length is less than 5, it will be 0. If not, it will be 1. So if you click send, oh, invalid. 0 if, sorry, I forgot the if. Sepal length less than 5, else 1. Then if you do this one, so the small sepal, it will be 1 if the sepal length is greater than 5. And if it is lower than 5, it will be 0. Okay. And maybe the last one that I want to explain is if we want to create the categorical data. Let's say I have the same formula. It will be 0 if sepal length is less than 5 and else 1. So I can make the category. If it is less than 5, I can make the category small. If it is higher than 5, I want to make category big. So I can put the values here, small and big. So if I send, then there will be a new column. And this new column will create new big and small, big and small like this. Okay, I think it's the time to finish. Any questions, comments? Okay, I will continue again on Thursday.